Hi, everybody. This is our second lecture or a primer, right? A guide to help you with these practice problems. Today we're going to do the dihybrid cross, right? And so this is problems 1 and 2 in the second section. And the dihybrid cross really is when we look at two traits at the same time. Now remember, Mendel said that traits assort independently. So this is really a way to illustrate that principle, his second law of genetics. All right. So anyway, it's funny. I looked at the problem set here, and the first dihybrid cross is really kind of hard. All right. Mom's a roller skating gum chewer. They're both dominant traits. She's heterozygous, so that's easy. And dad's a homozygous recessive skateboarder who likes Altoids, right? So, roller skating, we'll say big R is roller skating, little r is, what's that, skateboarder, right? Big G is gum chewer. Little g represents, likes Altoids, right? So this is the cross here, and you end up with a pretty messy dihybrid cross Punnett square. So forget that one. Let's look at problem 2. And you have my blessings to skip this. But if you think it will help you, you can run through and do problem 1 after you do problem 2. Okay, now in problem number 2, this is this kind of the classic dihybrid cross problem you would see on a test, whether it's in my classroom or even on one of the state's keystone tests, right? So mom and dad are both heterozygous for green polka dotted skin and orange and purple striped hair, both dominant traits, right? What are the odds they'll have children, et cetera, et cetera? So the first thing we want to do is get these genes out. So now we're looking at skin polka dots or skin color and hair color, right? And we say that green is dominant, and so we'll say this, that we'll use capital G to represent green polka dot skin, and little g for blue polka dot skin. Big O is for orange and purple striped hair. Little o is for red and green striped hair. All right, so that's the first step. And of course, since parents are heterozygous at both locuses or both locations, we end up with a Punnett square that's going to look like this, right? So mom's a heterozygote. She's got green skin and orange hair. She's heterozygous at both locations. Dad is the same. All right. Now the big trick here is with this problem is that, like, well, what kind of genes do they make? What kind of contributions do they make? Well, dad and mom both make 4 types of sperm and eggs respectively, right? So mom could have an egg that carries the big G gene her mom gave her and the big O gene her mom gave her. Let's assume that's what it is, right? And so this is one possible egg she would make. Another possible one is the big G little o. Another one is little g big O. And another possibility here is little g little o. And dad, of course, is going to make the same contribution. All right. Now, in this case, genotypic class ratios, we just don't care about. Okay. So let's get rid of that. What I do care about are the phenotypic class ratios. Okay. So you really only have 4 types of phenotypes, right? You're either going to be green and orange. You could be green and red, blue and orange, or blue and red. Does that make sense? All right. So for instance, when this sperm meets this egg, we've got a green and orange individual. All right. And then when you fill in these boxes, if you go down over here, I've got the blue and red person that fits in that box. All right. Now there's 16 possible outcomes, and that's sort of key to understanding this. And I want to show you something here, right? For this type of problem where both parents are heterozygotes, you're always going to see this 9 to 3 to 3 to 1 ratio. And we'll start off saying that the green and orange phenotype, we're going to make red all the time. I'll show you what I mean. Okay, well, I've kind of filled in my box here. And I've done some of it. And the first thing I did, when I start doing these crosses, and I'm very familiar with this thing, but what I want you to see is that for all of these particular matings, the person is always going to be green and orange in the end. That's what their phenotype's going to be. And it can have a couple different combinations. I could have two big G's, two big O's, two big G's, a no and a little O, a big G, little g, big O, of course, and then, or of course, the heterozygote, right? So they're always going to have that dominant phenotype. And look, 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 16 possible outcomes, all right? Next, let's look at the green and red class, right? So when this sperm meets this egg, I've got two big G's and two little O's, so they're going to be green and red, right? They'll have that homozygous recessive, what is it, hair color? Here's another green red. Here's another green red. 1, 2, 3. Now for the blue and orange, I'll color them blue, right? When this sperm meets this egg, I get a blue individual with orange hair. Same here, same here. 1, 2, 3. Yeah. And then, of course, last but not least, I have the single homozygous recessive at both loci to be fancy. That is, this individual has two copies of recessive genes for both traits. Okay. So remember that what the dihybrid cross is designed to do is to illustrate Mendel's second law that hair color and skin color aren't associated with one another. They can assort independently. Of course, the truth is we have lots of traits that are linked to one another, and hair color and skin color are often that way. But that really oversimplifies the process. Anyway, look, for these kinds of questions, hopefully it'll be a heterozygote versus a heterozygote cross, and you'll know that it's 1 in 16 chance to get this guy, 3 in 16 chances to get these two classes, and then last but not least, the homozygous dominant phenotype gives us 9 out of 16. For this classic 9 to 3 to 3 to 1 ratio, that's sort of it for the dihybrid cross. Thanks for your attention.